I'm Liz Smith, North Dakota Forest Service Forest Stewardship Manager, and this is part 3 of the Managing Mature Windbreak series. And today we're talking about how to conduct a windbreak performance assessment. In part 1 of this series, we defined a windbreak and we described a mature windbreak as one that has slowed rapid growth and is established. In part 2, we talked about what type of information to gather when scouting a windbreak and about some tree species and tree issues commonly seen in our mature windbreaks. Now we are going to talk about how we can take a critical look at how well the windbreak is performing its job and consider what factors are influencing job performance. This presentation is part of the North Dakota Forest Service's Forestry Friday series. Windbreaks work by altering the flow of wind, but what does this mean? In a place like North Dakota, we don't have a lot of natural features that cause turbulence, so our winds can often speed unchecked across acres of relatively flat ground. The horizontal extent of the windbreak effect, upwind and downwind, is usually proportional to the height of the windbreak. Reductions have been measured as far out as 50 times the height of the windbreak, but most reductions occur out to about 20 to 30 times height. There is a triangular quiet zone that extends from near the top of the windbreak to near ground level at about 8 times the height on the leeward side. Above and downwind this zone is the wake zone. The effect of the quiet and wake zones is to create turbulence, which slows or breaks up the wind and decreases its ability to carry particles of soil or snow, to dry out crops, damage buildings and equipment, and just generally make plants, humans, and livestock miserable. This basic schematic shows wind encountering a windbreak, getting basically shaken up and slowed, and then picking speed up again on the other side of the windbreak. This is the logic behind field windbreak systems. Each windbreak is placed at a distance about 20 to 40 times the height that the trees are expected to reach at maturity. This way, just as the wind gets a chance to speed back up again, it encounters another windbreak, and the benefits of the altered wind flow are distributed across the entire field. So whereas height determines the horizontal distance that the windbreak is effective, density controls the velocity reduction and how long that reduction is sustained. Various different windbreaks have different densities depending on the materials used. Or in the case of vegetative windbreaks, species used, number of rows, row spacing, and factors like the condition of the windbreak. 4 basic windbreak scenarios are presented here, ranging from low density to high density, with the bottom scenario being a 100% solid fence. But that could be a house or a barn or anything that wind cannot pass through. Here is a graphical representation of these 4 scenarios, all assuming that the windbreak is the same height. The yellow line, or solid windbreak, results in a steep drop in velocity, followed by a fairly rapid rebound. The lowest density windbreak, the blue line, doesn't result in as sharp of a reduction, but also doesn't bounce back as fast. The reductions are sustained better compared to the 100% dense windbreak. The mid-range density scenarios get nearly as steep of a reduction, but with the reduction sustained over a greater distance. But of course, it can't be just that simple. Windbreak density can change depending on the season. Take, for example, a deciduous windbreak, which may be up to 70% dense or more in the summer when the leaves are on, and may drop to 30% in the winter. And of course, height varies from species to species, and certainly varies during those first years when a tree is growing. which in turn influences the distance that the velocity reductions are sustained. Wind is, of course, usually invisible, but the effects of wind can easily be seen. Soil becomes airborne, tender crops are dried and abraded, and in North Dakota, we tend to get some snow, and we certainly get a lot of wind to carry our snow around. Windbreaks are an essential tool for managing wind-driven snow. A snowdrift forms in the eddy created on the leeward and to a lesser extent the windward side of the windbreak. As we previously discussed, height is an important factor in the horizontal effectiveness of a windbreak, and density heavily influences that pattern of wind velocity reduction. When wind is accompanied with snow, the height and density of the windbreak will determine where the snow drifts and how big the drift can become. So if the goal is to spread snow evenly across a farm field, a lower density is needed. A high density windbreak would result in a deep drift adjacent to that field windbreak, which would not meet the purpose. So why would we ever want to make a big drift? In a farmstead scenario or along a roadway, we want to make a big drift because big drifts hold a lot of snow that won't be blowing around. But we want those big drifts to be located out of our way. A properly functioning windbreak will trap and store snow where we want the snow to be. So let's look a little more closely at two of these diagrams, the Wyoming slatboard snow fence and a 60 to 80% dense multi-row windbreak. Both of these windbreak designs offer about the same amount of storage capacity, and the slatboard fence will offer this amount of snow control immediately after installation. The tree windbreak might take some years to reach this level of performance, but maybe 20 feet in height isn't its maximum height. If the windbreak will continue to grow taller, then we know that the windbreak effect will be felt a further distance from the windbreak. Plus, board fences are much more expensive to install and require costly replacement and repairs continuously. A tree windbreak is comparatively cheap to install, and after those first couple of years, should really only require minimal, inexpensive preventive maintenance over its lifetime. Plus, tree and shrub windbreaks offer all those extra benefits. I'd like to see a board fence do that. I'm just kidding there a little bit. There are places where trees and shrubs will not work for a windbreak. That is true. But there are lots of places that are well suited to growing trees, and vegetative windbreaks can be considered in those situations. So actually calculating density is really difficult because from a strictly aerodynamics point of view, windbreaks aren't flat. They're three-dimensional structures of leaves, twigs, and branches, and even the trunks that influence how air moves through them. Optical density is really the only practical tool we have to measure windbreak density. Look at the windbreak straight on from the location you are wanting the windbreak to protect. Imagine the sky as white pixels and the windbreak as black pixels. What is the ratio of white to black? It takes practice, but eventually you will be able to come up with an estimate of density on the day that you are there. If the trees are deciduous and fully leafed out, try to imagine the windbreak in the winter without any leaves. Whether or not a windbreak is dense enough or not dense enough is really a matter of the purpose of the windbreak. Windbreaks are designed to alter the flow of wind and manage wind-driven snow. So winter can be a great time or a terrible time. Winter can be a great time to look at windbreak function. Is the windbreak catching and holding snow where you want it to? Or is snow escaping the collection area and being captured in a place where you don't want it? And this is again where this density discussion comes up. The same windbreak that is actually doing a great job of spreading snow across a crop field may be completely inadequate to protect a farmyard. When we scouted the windbreak, we tried to find out the age. A young windbreak may still be gaining density and height and may be trending in the direction that we need it to. When we scouted, we also looked for signs of natural regeneration. A mature windbreak with little natural regeneration is unlikely to gain density. It's most likely trending the other way and will continue to lose density. As part of our scouting, we noted the locations of structures and other things the windbreak should be protecting. Windbreaks perform optimally against winds hitting it perpendicularly, but wind doesn't always come from the same direction. And wind also sort of curves around the edge of the windbreak, decreasing effectiveness in the ends. So in North Dakota, we recommend extending the windbreak 200 feet beyond the area needing to be protected. An L-shaped windbreak has the advantage of being effective against winds coming from a range of different directions compared to a single leg windbreak. The continuity of a windbreak influences its efficacy and longevity. Gaps in a windbreak create a funnel, and through this funnel, the wind flow is concentrated with velocities often exceeding open field wind velocity by 20% or more. Increased wind speed also damages the trees on either side of the gap, which can lead to widening of it and further degrade the windbreak's effectiveness. When we scouted, we looked for localized gaps or breaks in the windbreak, but we also looked for individual missing trees. So we've scouted and we've thought about how the windbreak is performing. We've tried to determine the density using an optical density assessment. So let's recap. What were the goals for the windbreak? Is it working well? Could it be working better? And what way is it trending? Ask the landowner what their experience has been with managing the windbreak and observe what they've been doing to manage it up until now. What was the original purpose of the windbreak? Is it still needed for that purpose? How well is it performing? What species are present and what is their condition? Do the trees and shrubs appear healthy? Is the condition variable from row to row? Are there dead trees or shrubs, and are they distributed throughout, or are they localized to one spot in the windbreak? What is the age of the windbreak? Is there any natural regeneration occurring? What species are regenerating? Damaging events. Has the windbreak been subject to an extreme event, such as flood, fire, or high wind? Is there evidence that cattle or other livestock have been in the windbreak? What are some site limitations? What are the characteristics of the site that might limit windbreak potential? And we've sketched the windbreak, noting things like in-row spacing, between-row spacing, tree height, locations of troublesome snowdrifts, standing water, old feedlots, steep terrain, buildings, roads, other structures, property lines and adjacent land use, and of course, any overhead power lines, easements, or setbacks. So now we have gathered all of this information and we're ready to make a plan for how we, the Windbreak's human caretakers, can help the Windbreak be its best self so that it can continue to perform its job into the future. Next up in this series about managing mature windbreaks, we're going to talk about windbreak renovation techniques.